Hello, welcome to topic 7.10, the reaction quotient and how it relates to Le Chatelier's principle as part of the AP Chemistry Unit 7 on equilibrium. My name is David Decker, and I'm an AP Chemistry student and a junior from Bayport High School in Green Bay, Wisconsin. Let's get started. So before we dive into this topic, we must recall a few terms. The reaction quotient, or Q, is the value of the concentrations or pressures of the products of a reversible reaction over those same values for the reactants at any point during the reaction. The equilibrium constant, or K, is the same calculated value except only when the reaction is at equilibrium. In the picture, we can see how the value of K is expressed by an equilibrium expression according to the reaction given. Remember that the value for any reactant or product is always raised to their stoichiometric coefficient. This concept was learned in topic 7.3. We must also recall the concept of Le Chatelier. Le Chatelier's principle states that when a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. Changing the concentration, volume, or temperature of a chemical system will result in a shift to equilibrium. The reaction will shift left or right according to whether more reactants or products need to be made in order to keep K constant and reach equilibrium again. This concept was learned in 7.9. So the values of Q and K are expressed in Le Chatelier's principle because when a system is at equilibrium, it means Q and K are equal to each other. When that system is disturbed, Q is no longer equal to K, so the reaction is no longer in equilibrium. The reaction will then shift in a certain way to bring Q back to equaling K. This pertains to both the concentrations of the particles in a system and their pressure, which is expressed by a C or P in subscript with Q and K. Note that because it depends on pressure, this concept only applies to particles that are in a gaseous state in a chemical system. Now, consider this following reaction. When the concentration of, let's say, the products is changed by adding more NO2 into the system, its concentration changes and equilibrium is disturbed. There are now more products that will make more reactants. The reverse reaction rate increases. This means that the reaction will shift to the left to account for the disturbance by making more reactants. But how is this represented by Q and K? Here's the chemical reaction expressed graphically. When the system is at equilibrium originally, the values of the concentrations are constant. In the equilibrium expression, plugging in the concentrations at any time for Q will equal the value of K at equilibrium. But then, more NO2 is added to the system, increasing its concentration. The concentration of NO2 increases, so the numerator and therefore the value of Q also increases. With a higher concentration of products, Q is now greater than K. The system responds by increasing the reverse reaction rate because then more products of NO2 will be used up, which decreases its concentration, in order to make more reactants of N2O4, increasing its concentration. This is seen in the graph as the concentration of reactants in red goes up and the concentration of products in blue comes back down until the system reaches equilibrium again. At that point, Q is now equal to K. What we learn here is that when Q is greater than K, the products are greater and the reaction will shift to the left. A similar process happens if the reactants are increased. Once N2O4 increases, the value in the denominator increases, which decreases the value of Q. Since there are more reactants, the system shifts to the right to make more products. The concentration of reactants decreases and the concentration of products increases, bringing Q back to equal K. When Q is less than K, the reactants are greater and the reaction shifts to the right. Note the text in red, which points out that both the original and new state of equilibrium actually have different values for each of the individual concentrations of each particle. This is seen in the graph. The original and final concentrations for the reactants do not line up, and neither do the products. However, K is calculated to be the same value for both states. This is shown as the reaction having different equilibrium positions, but the same equilibrium constant. From this, we can remember these rules. Increasing the concentration of one or more of the reactants means Q is less than K and causes the reaction to shift to the right. Increasing the concentration of one or more of the products means Q is greater than K and causes the reaction to shift to the left. Decreasing the concentration of one or more of the reactants means Q is greater than K and causes the reaction to shift to the left. Decreasing the concentration of one or more of the products means Q is less than K and causes the reaction to shift to the right. What about when pressure is changed? Consider this reaction given. Let's say that the volume of the container that the system is contained in decreases. This means that the pressure of the molecules increases. The reaction's value of Q is now unequal to K. To solve this, we must instead look at the stoichiometric coefficients of the reaction to figure out how it will shift. For this reaction, it will shift to the side with fewer moles of gas particles to decrease the total amount of particles in the container. Fewer particles means this pressure decreases as well, bringing the system back to equal K. So here's a diagram of how you can count the moles of gas particles in the given reaction. When the pressure increases, the reaction will shift to the side with fewer moles, which for this reaction is the product side. That means the numerator will increase and the denominator will decrease until Q equals K. If pressure decreases, the reaction will shift to make more moles to increase the pressure. This reaction will shift to the left, increasing Q to equal K. Note how the stoichiometric coefficients are expressed as exponents in the equilibrium expression. From this, we can remember these rules. Decreasing the volume causes the reaction to shift in the direction that has fewer moles of gas particles. Increasing the volume causes the reaction to shift in the direction that has more moles of gas particles. In addition, if a reaction has an equal number of moles of gas on both sides of its equation, then a change in volume produces no effect on the equilibrium because the system cannot shift to change the total number of molecules. Similarly, adding an inert gas to the system produces no effect on its equilibrium because it does not react with any of the particles. Changing the temperature also causes a change in equilibrium, but while the other factors so far have caused Q to change, a temperature change causes the equilibrium constant K to change. This is because heat is absorbed or released by the reaction itself, so adding more will increase the rate of one side of the reaction. In an endothermic reaction, the forward reaction absorbs heat. This means that heat can be thought of as a reactant. However, in an exothermic reaction, the forward reaction releases heat, meaning that the reverse reaction absorbs it. Heat can be thought of as a product. So just like increasing the amount of reactants will increase the forward reaction rate, increasing the heat will have the same effect. When heat is added to an endothermic reaction, the forward reaction rate increases. As the reaction reaches equilibrium, it favors products more, so K increases as well. When heat is added to an exothermic reaction, the reverse reaction rate increases. The reaction favors reactants more as it reaches equilibrium, so K is smaller than before. From this logic, we can learn these rules. Increasing the temperature causes an endothermic reaction to shift right, and K increases because heat is a reactant. Decreasing the temperature causes an endothermic reaction to shift left, and K decreases because heat is still a reactant. In an exothermic reaction, increasing the temperature causes it to shift left, and K will decrease because heat is a product. Decreasing the temperature causes an exothermic reaction to shift right, and K increases because heat is a product. Here is an AP example problem regarding the concentrations of a system at equilibrium. It reads that a mixture of NO and Cl2, both gases, are placed in a container and allowed to reach equilibrium according to the chemical equation shown above. At equilibrium, the reactants and products have the concentrations listed in the following table. Which of the following is true if the volume of the container is doubled? Please pause the video at this point to attempt this on your own, and then continue watching for the answer. The correct answer to this problem is A. An interesting part of this question is that the disturbance to the system is the volume being doubled, so we may think that at first the question is about pressure. However, the volume being doubled will reduce the concentrations by half for all of the gaseous particles, which is every component in the equation. Then we must write an equilibrium expression and plug in the new halved concentrations to solve for Q. Q is equal to 2000, and since that is greater than K, the reaction will shift to the left towards the reactants. Here's our second AP example problem. The system represented by the equation above is allowed to establish equilibrium. The initial pressures of the substances are given in the table. Which of the following explains what the system will do as it reaches equilibrium? Please pause the video at this point to attempt this on your own, and then continue watching for the answer. The correct answer is D. So at first glance, this problem could involve using a Rice table to solve for the partial pressures at equilibrium. But the answers given only describe how Q relates to K. Because of this, you need to identify the correct equilibrium expression to solve for Q, and then whether that is less or greater than K given the values. When you plug in the initial partial pressures and use the correct stoichiometric coefficients for Q, you get 20, which is less than K. That means that the reaction will shift to the right and produce the product NOBr. D is finally the correct answer because the expression is written correctly with stoichiometric coefficients. What should we take away? The response of a chemical system to a disturbance relating to Le Chatelier's principle can be expressed with the values Q and K. A disturbance to a system causes Q to differ from K, and the values allow us to predict which way the reaction will shift in order to bring Q back into agreement with K. Changing the concentrations or pressures of a system causes a change in Q. Changing the temperature causes a change in K, because heat is absorbed or released as part of the reaction. Thank you for taking the time to learn section 7.10 with me, and I hope that this video was helpful for you.